All right, folks, good morning. Happy Monday. We are going to start off with some announcements. So I'm going to go ahead and share my screen so we can take a look at the announcement that was posted on Canvas yesterday. All right, so the first part of the announcement from yesterday was just letting you know that some of the exams have been graded and some of them have not, but it will be graded by the time exam 4 rolls around. So it should be graded by the end of this week if you don't have yours graded yet. Also, in terms of the structure for exam 4, we're going to keep it very similar to exam 3. I know there was some initial anxiety around that, but most of the feedback that I've gotten has actually been pretty positive around it. So I'll take that for what it is. And last but not least, if you have any pressing questions, feel free to reach out. I will not be opening up check-ins like I have the last few exams, just because we're kind of getting down to the end and there's definitely a lot of work that I need to do in terms of grading and preparing the last few lessons. But if you have like a pressing concern, please feel free to reach out. All right, so believe it or not, we are down to our last 2 weeks. In fact, we only have 6 more lectures, which is pretty crazy. But this week, we're going to cover 11.2, 11.3, and 11.4. I don't think we'll be able to finish all of 11.5, so I decided let's just save that for the final exam and not for this exam. So we'll only be going through 11.4 for exam 4 this Thursday. You have 2 quizzes that are due this week. The first quiz is due Wednesday morning by 9:30. That is quiz 12. And then quiz 13 is due Friday morning by 9:30. Okay. I know that that quiz is due around the same time as your exam. I would really encourage you to get it done in advance just so that you feel more prepared for your exam. Okay. That's it for this week. And then next week, we are going to cover 11.5, 11.6, and 11.7. We'll have 2 last quizzes. Quiz 14 will be due Wednesday of next week, and quiz 15 will be due Friday of next week. And your final exam will be on Thursday, August 6th. So that's it in terms of announcements. Does anyone have any questions on the announcements?
Will the final be pretty much the same format as the exams?
Yeah.
Okay, thank you.
You're welcome, Abby. Any other questions? Yeah, I'll be sending out an email about the final probably at the end of this week. And that final will be cumulative. So it is going to cover all of the topics that we have gone through this summer. There will be a more structured list of these are the topics you should study and these are the ones that are maybe a little bit less important for your success in the next course. So you can look forward to that at the end of this week. For the final, are we having more time? Probably not. It's meant to be a 2-hour exam, so anything above that is already sort of extra time. Any other questions right now? Your cheat sheet needs to be handwritten. It can only be double-sided, so you can use pieces of your old one. But I think I would really encourage you to craft a new one for the final, because I think that, you know, the more that you write something, the more that you process it and actively generate that document, I think the easier it is to connect between that and the questions on the exam. All right. Well, if other questions come up, we can talk about it later. We can talk about it tomorrow. So I'm going to go ahead and stop sharing this screen and go ahead and we're going to pull up the 11.2 notes and we'll get started. Okay, so let's get started. We are going to be talking about convergent and divergent infinite series, okay? So let's start with what we know, and then we'll talk about what's new. We'll go through some basics, and the main theme of today is really going to be taking a look at 3 special types of series, okay? Tomorrow's lesson is going to be more about more general types of series, but today we're going to look at 3 very special cases, okay? So what do we know? We know that a sequence is nothing more than a list of numbers written in a specific order. So we learned about that last week. And we know that some sequences can be considered infinite sequences, and that even though there are an infinite number of terms in the sequence, infinite sequences can converge, meaning that the right end behavior flattens out to a horizontal asymptote, like it sort of approaches a numerical value, okay? And we also know that these infinite sequences can sometimes diverge, where that right end behavior goes to positive infinity or to negative infinity, okay? Meaning it doesn't flatten out, but it goes up or it goes down. So when we are looking at infinite sequences, why is it that we only look at the right end behavior?
Because n is a positive integer.
Yeah, because n is a positive integer, right? So exactly, when we're looking at n behaviors, we really want to focus on that right end because we're looking at the sequence as it goes all the way to the positive infinity, the infinite in the very, very last term at the end of this infinite sequence, okay? So what's new? We're going to be talking about series, okay? So sequences are very similar to series, but it's really important that we understand the differences between the two, okay? So in a series, instead of just having a list of numbers written in a specific order, we actually add the terms in a sequence. Okay, so we are going to be adding the terms in a sequence. Now, this can come in sort of 2 different forms. We can have what we call partial sums. And a partial sum is nothing more than adding some of the terms. So for example, maybe I have a sequence and I want to add the first 3 terms, that would be considered a partial term. Or if I wanted to add the first 5 terms, that would be considered a partial term, a partial sum, okay? But on the flip side, we're actually going to be spending a lot more time looking at infinite series, okay, or an infinite sum. And what that means is we're not going to be adding some of the terms together, but we're going to be adding all of the terms together. So we add all terms in the sequence. Okay. Now, when we add all the terms in the sequence, one of two things can happen. Our series, because that's what it is when we're adding them, our series can converge, meaning if I add up every single term in a sequence, I actually get a number. And so that would mean that my series converges. Or I might add up all the terms in the sequence and I get infinity or I get negative infinity. And that would be a case where the infinite series diverges. Okay. So the idea of series is just a little bit different than the sequence because we are adding all the terms together. Okay, so we're not just looking at each individual term, but rather we're looking at adding all of those together and seeing what happens. Okay. So we've got sequences and we've got series. So let's take a look at some of the basics. Okay. So we use this little lowercase letter s, okay, this little s right here. That s is referring to a series, okay? Now, how do I know that? Well, the first one, you're not really sure because it says s1 equals a1. But as we kind of move down, s2 means I have to add the first term and the second term. So I'm adding things, so it's not a sequence, it's a series. S3 means I take the first three terms and I add them together. S4 means I add the first four terms together, okay? And I can keep going until I get to whatever it is that I'm looking for, let's say S sub n, okay? So if I want S sub n, then I'm just gonna add the first nth terms. So this part is add the first n terms. Okay. Now this sigma notation, which should be familiar to us, okay, this sigma notation right here, this is our fancy way of saying sum, okay? So textbooks kind of write it like that. I cheat a little bit. I just write it kind of like a pointy E. So I write it like 1, 2, 1, 2, 3, 4. Okay, so that's how I write it. Some people like to write it more like the textbook and be fancy and have little things there. I think when I'm doing a problem with a sigma notation tends to be a lot of work, and so I'm not as invested in writing the symbol the second way. I kind of write whatever's faster, and so again, like it's just kind of a 1, 2, 1, 2, 3, 4. Okay. So anytime we see this sigma notation, that refers to a sum. It means we need to add a bunch of things, okay? And so the bottom number here, I equals 1, tells us where we're going to start, and our top number, n, that tells us where to stop, okay? So if I'm looking at a partial sum, I really want to think about using this for a partial sum, right? Because I'm only adding up to a certain number. However, when we start to look at taking an infinite series, it means that we need to not just add up the first 5 terms or the first 100 terms or the first 1,000 terms, but we're actually adding up every single term, meaning we're starting at 1, okay? And we are ending at infinity, all right? Now, in this course, we are going to have the infinity on top, all right? Now, if you go on further in math and when you see series again, sometimes it's sort of implied that it's an infinite series. So if you see something like this and you have your a sub I here, and there's no top and bottom numbers, that is implied that it's an infinite series, okay? The truth of it is mathematicians get very lazy and they're like, well, if we're all just talking about infinite series, let's just leave it all out, okay? So this might be something you see in the future, and you can consider this shorthand for infinite series, right? Like I said before, though, we will use the infinity symbol. So I don't expect you to know that now. I don't expect you to use it now, but in the future, if you choose to go down that path, that's just why people just get a little lazy and they don't want to write the top and the bottom numbers, okay? Carlos, great question. Will it always be starting at 1? And the answer is no, okay? So this bottom part right here where it says I equals 1, sometimes we start at 1, sometimes we start at 0, but you could also start at 2, 3, 4, okay? So the bottom number, you just have to be careful when you're looking at our particular series. So we'll look at like writing out values and then it'll make a little bit more sense, but it could be 1, it could be 2, it could be a different number, okay? So this does not have to be 1. All right. Any questions on the notation so far? Okay. So here are some other notations that you might see, okay? So again, this bottom number, right? In this case, the bottom number is 0. So it's okay for it to be 0. 0 is another very common starting point, okay? So 1 and 0 are kind of our common ones. We know it's an infinite series because the top number goes to infinity, okay? Now, one quick thing, this letter right here, whatever letter you have in the bottom, it should match the letter that is in your equation, okay? So like if I have I equals 0 on the bottom, then I want to write 3 over I squared plus 1. And that I does not mean like imaginary, it's just an I, okay? But really, I could use any letter I want. So let's say I wanted to use K. That means I have to have a K in my equation. Or what if I wanted to use N, which is going to be the one we're going to use the most? You want to have the N in the equation, okay? So kind of like when we're taking integrals and we need everything to be x's and dx's and separate from y's and dy's, we really want to keep everything with the same letter as we're writing our infinite series, okay? So this is the one we will use. All right, we will use this one mostly with the ends. But just to let you know, like in case you're watching some other videos or you have a different professor or you just see it in a different format, anytime, as long as the number or the letters match, you're still going to be fine. It's still going to be an infinite series, okay? So let's take a look at some special cases. Okay, so that's the theme for this first part here today. We're looking at special cases of infinite series, okay? We're gonna take a look at 3 special cases in particular. We are going to take a look at the geometric series, okay? And we'll do a few examples with the geometric series. We are going to take a look at something called the telescoping series, which I think is actually pretty cool. It's not as scary as it sounds. And then we're going to take a look at positive term series and harmonic series. Okay. So those will be our 3 special series for today. All right, so let's start with the geometric series, okay? Now, way back when you took pre-calc or maybe even 96, actually, I don't know if this is in 96, but you learned about patterns of numbers. And so there's sort of one set of pattern of numbers where you could like add the same amount every time, or you could subtract the same amount. So for example, if you had like 5, 10, 15, 20, what am I adding every time?
Multiples of 5.
I'm always only adding 5, right? Like I'm not adding multiples of 5. It's always just 5. Like from 5 to 10 is 5. From 10 to 15 is 5. From 15 to 20 is 5. Okay. So we're adding 5 every single time. And we could also just subtract 5 every single time or whatever number that is. But when we have something called a common difference, okay, that gives us what we call an arithmetic series. But what we're looking at is a geometric series. And so a geometric series, we don't add the same number every time, but in fact, we multiply by a given number, okay? So instead of having what we call a common difference, we should see a common ratio or a number that we multiply by every single time. Now, a geometric series is actually it's very similar to our exponential functions. And the general form of an exponential function is y equals ab to the x power, okay? So in general, when we see something that looks like ab to the x, I want us to be thinking this is not just an exponential function, but when it has the sigma notation, we're actually looking at a geometric series. Okay. So this a over here, right? A is usually your starting value. Your b, we're actually going to call that r, okay? Our r or our b, that is the common ratio, okay? So let's just take a look at example 1 and example 2 real quick. What is the starting term in example 1?
5.
Mm-hmm. What's 5? Is it 5 for both of them? Example 1 and example 2?
Yes.
Yeah, okay. What about the common ratio for example 1?
1.5 for the first one and 2 for the next one.
How about 1/2, not 1.5?
My bad.
Yeah, okay. That actually does make a difference, okay? So it's really important we know that that first ratio is 1/2 because it's less than 1. And the second one is 2, it's greater than 1, okay? So this number and this number are going to be valuable in helping us determine whether the series converges or diverges, okay? So here's how this works for geometric series. If your common ratio, okay, if your absolute value of that common ratio, because sometimes we work with -1, but if the absolute value of r is less than 1, then what that means is your series converges. Okay. So R is less than 1 means that your series converges. And more specifically, this is one of the few series where we have a very nice formula to find the sum of that series. So see where it says find the sum, we actually have a formula for that, but this formula is only true for geometric series. You can't use this formula for any other kind of series, only for geometric. And the formula is S equals, we take our starting term, so whatever our starting term is, we put that in the numerator. And in the denominator, we do 1 minus your common ratio. And when you simplify all of that, you will get the infinite sum, the number that this series converges to if it converges. Okay. So given that information, in this particular problem, we have a situation where our common ratio is 1/2, and that is less than 1, right? 1/2 is less than 1. That means our series converges. And if we want to find the sum, we can say a sub 1, which means we plug 1 into this equation. Okay? So I plug 1 in. What value do I get out?
2.5.
Sorry, what was that?
5.
5. Yeah, when we plug in 1, we're going to get 5 out. And so that's the number that goes up here. Okay? So that's what we mean by a sub 1. We mean plug in the first term, and whatever number comes out, that value goes in the numerator. In the bottom, we have 1 minus 1/2. Okay? So that is going to give us 5 over 1/2, or 5 times 2, or 10. So as crazy as this seems, what this means is if I take this series and I add up every single term, 5, what's the next term? 5 is the first term. What's the second term?
5.5.
5 halves. Yeah, exactly. 5 over 2. What's the next term?
5 over 4.
5 over 4. Okay. So if I take 5 and I add it to 5 halves, and I add it to 5 fourths, and I add it to the next one would be 5 eighths, yeah. And I keep going. I add up every single term. It's going to add to 10. Pretty crazy that you could sit and add up every single term in a sequence and you would end up with a number, okay? But geometric series are very special like that. Not all series converge, first of all, and the ones that converge, not all of them have a straightforward formula to find out what it adds up to, okay? So in contrast, what can we say about example number 2?
Divert.
Yeah. So if your common ratio is greater than 1, that means it's going to diverge. Okay. And if it diverges, then it means that there is no sum that we can find. Okay. So in this case, we have our R is 2. 2 is greater than 1. So this series diverges. Okay. Now, just for kicks, let's kind of write out a first few of the terms here. So the first term is 5. We agreed on that earlier. What's the second term in example number 2?
10.
10, good. What's the next term?
15.
Nope, not 15.
20.
20, yep. What's the next term?
45.
40.
40, yeah, I'll take 40, right? How are we getting from each term to the next one?
Doubling.
We're doubling it, right? So we do 5 times 10, or 5 times 2 gives me 10, 10 times 2 gives me 20, 20 times 2 gives me 40, right? And even just by writing out the first 4 terms, I can tell these numbers are going to get larger and larger and larger and larger, which means that when I add them all up together, they're not going to equal a number. They're going to go, in this case, not to negative infinity, but to positive infinity, okay? All right, any questions about geometric series? Okay, so let's try a couple more examples, okay? So let's take a look at example 3. It says, determine whether this series converges or diverges. If it converges, find the sum, okay? So what's happening in example 3? How do I get from 2 to 2/3? And then from 2/3 to 2/3 squared?
It exponentially gets smaller.
Multiply by a ratio of 1/3.
Yeah, it is exponentially getting smaller, but let's be more specific here, right? Because we need to tell whether it converges or diverges. And so in this case, if I multiply by 1/3, I'm going to get the next term. If I multiply by 1/3 again, do I get 2/3 squared?
Yes.
Yeah, okay. And then I could keep going. And so if I'm multiplying by 1/3 every time, what that means is my ratio, common ratio, is 1/3. Okay. That means this series converges. And that means that I can find the sum as long as I plug it into my a sub 1 over 1 minus r. Okay. What's my a sub 1 in this case?
2/3. 2.
2.
Okay. So let's keep in mind that a sub 1, it means the first term in the sequence. Okay, so by convention, we kind of choose it to be a sub 1, but it could be a sub 0, depending on how you're counting. So whatever the first term is, that's what goes on the top. And so in this case, we have 2. And then in the denominator, we have 1 minus 1/3. So that's going to give me 2/2/3, which is 2/1 times 3/2. Those reduce. And so if I sat and added up every single term in this sequence to get the infinite series, I would get a sum of 3. Now, let's just for kicks practice writing our notation. So let's say we wanted to write this with sigma notation. I could start with a sigma, okay? And because I said we're going to choose sort of the n notation by default, we're going to write n equals. And then because I know this is an infinite series, I can put infinity on the top. So I'm starting at a certain value, I'm going to infinity, okay? What is my starting term? My starting term we said was 2. The common ratio is 1/3. And if I put an n here in the exponent, and I start at 1, do I get the first term in my sequence?
No.
No. Okay, so how do I modify that equation so that I get a 2 out for my a sub 1?
Start at 0.
Sorry, say that again?
Start at 0.
You could start at 0. That's one way to do it. How else could we do it?
N minus 1.
Yeah, so we could do n minus 1. That's one way to give you the term you want. Or we could do n equals 0 to infinity of 2 1/3 to the n. Okay. But I think we all agree that both of these series give us the same sequence or the same series, right? I get a 2, a 2/3, a 2/3 squared, 2/3 cubed. Both of these work. So this right here is a topic I hope we have time to come back to either later this week or next week. This is called an index shift. Okay, so the index shift means that you have like this could be shifted down to n minus 1. But if you shift the powers, you also have to shift the index at the bottom. Okay, so if your power is n, your bottom should start at 0. But if your power is n minus 1, you should start at n equals 1. Okay. That, though, is, again, something that you probably won't need again until differential equations, but I think it's an interesting way to look at the different ways you can set up the equation. Okay. All right, let's take a look at example 4, okay? I know that this gives us terms in decimals, but I actually always find it easier to find common ratios when we're looking with fractions, okay? So let's think about how we get from 0.6 to 0.06.
Times 1/10.
1/10, right? We're just moving that decimal place one place to the left. And then let's make sure that this is in fact what's happening. If I go from 0.06 to 0.006, yeah, I multiply by that 1/10 again, okay? So that confirms for me that my R is 1/10. So converge or diverge?
Converge.
Converge.
Good. And S equals, what number is gonna go on the top?
6/10.
Yeah,
0.6.
yeah, 0.6 or 6/10, and in the bottom I have 1 minus 1/10. So this will give me 6/10 over 9/10, which is the same as 2/3. And so in this case, because as someone mentioned earlier, this is an exponentially decaying situation, or we say that it's a geometric sequence that is decreasing, then we can find the sum and we can say, hey, if you add them all up, you're going to get 2/3. Nothing bigger, nothing smaller, you're going to get 2/3, okay? But this only works when it's geometric and if that ratio, the absolute value of the ratio, is less than 1, okay? All right, so in a nutshell, that is geometric series. Any questions about that? I think the geometric series is pretty straightforward. It's more just remembering what the features are that tell us if it's increasing or decreasing, and being able to recognize it, that it is indeed a geometric series. Okay. But now let's take a look at something called the telescoping series. I think this is one of my favorite ones because it's pretty cool how you can sort of work through these problems. So let's see, determine whether a sub n equals 1 over n times n plus 1, where n is greater than or equal to 1. Let's see if that converges or if it diverges. And if it converges, find the sum. So again, to kind of practice the notation, let's take this and let's write it in sigma notation. What's my bottom number going to be?
1,
1. Good. How did you know that?
because it's greater than or equal to 1.
Good. And we're looking at an infinite series, so the top is going to be infinity. And then what goes here is just my a sub n, 1 over n times n plus 1. Okay. And if we were to write out the first few terms in the series, let's plug in 1. We get 1 over 1 times 2. When we plug in 2, we get 1 over 2 times 3. When we plug in 3, 1 over 3 times 4. And we keep going. And it's always n times n plus 1. And we keep adding that until we get to the end. Okay. Now, when we look at it in this particular format, I can tell that the numbers are getting smaller, but I don't exactly know what is happening in terms of like, what does it converge to? Okay, so I kind of have an idea it's going to converge because my terms are decreasing, but I have no idea what it's going to converge to in terms of a sum, because I can't use the 1 over, or the a sub 1 over 1 minus r. I can't use that because it's not a geometric series. So what we're going to do is we're going to bring back our good old friend partial fraction. Okay, and so we are going to take what we know about partial fractions, and we are going to rewrite this with partial fractions. Okay. Now, the good news is with the telescoping series, the partial fractions are actually not that hard. We just have to remember the setup and we have to work through a few things. Okay. So we've got 1 over n times n plus 1 equals, how do I set up my partial fractions and how many are there going to be?
1 over n plus, a over n plus b over n plus 1.
Yeah, so I'd have 2 partial fractions. My denominators are just linear, so my tops are going to be constant. And nothing's repeated, so I don't have to worry about taking care of more than one of those terms, okay? So if we jump right to the step where we have sort of already crossed out the denominator, we'd get 1 equals, what do we multiply a by?
N plus 1.
Yeah, n plus 1, and then the b gets multiplied by the n. Okay. Good numbers to choose for n.
0.
0 and
-1.
-1. Okay. So when I plug in 0 for n, I will get 1 equals a. When I plug in -1 for n, I will get 1 equals negative b, or b equals -1. Okay. And what that means is I can write my original expression as 1 over n minus 1 over n plus 1. Does that make sense to folks where I got the minus 1 over n plus 1 from? All right, so here's what I'd like us to do now. We're gonna take all this stuff that we did with partial fractions, okay? So what we've done is create a new way to write out a few of the first few terms, okay? So just like before, we're gonna take our sigma, n equals 1 to infinity, but instead of writing 1 over n plus n, 1 over n times n plus 1, I'm going to write it as 1 over n minus 1 over n plus 1. Okay, so these two, this and the other one in the red, are the same expression. I just rewrote it using partial fraction. So now this is the cool part. Let's plug in 1. 1 over 1 minus 1 over 2, okay? Plus, because I have to add what happens when I plug in 2. 1 over 2 minus 1 over 3. Plus, what do I get when I plug in 3?
1 over 3 minus 1 over 4.
Perfect. Okay. So now I'm going to just put a plus and a dot, dot, dot. Now when I get all the way to the end, the last one will be 1 over n minus 1 over n plus 1. Okay. So let's check this out here. Before we go crazy trying to find some common denominators, right? Let's take a look at the bigger pattern here. I have 1, and then I have a minus 1/2. But in the very next term, I have a plus 1/2. So minus 1/2 and plus 1/2, those go to 0. Now keep going. Minus 1/3 plus 1/3. Well, shoot, that goes to 0 too. I see a minus 1/4. Will there be a plus 1/4 in the next term?
Yes.
Yeah. And so that means all of these terms in the middle, including this 1 plus n, go to 0. So even though I have an infinite number of terms, the first one is there. Everything in the middle goes to 0 until you get to the last term. Pretty crazy, huh? That you could write this and think, oh, I have an infinite number of terms. How am I going to write them all out? But it turns out everything in the middle cancels. So we really only have 1, which is the first term, minus 1 over n plus 1. Okay. Now, we are going to find the sum in just a little bit, but let's go ahead and turn this into a single fraction first. So we will get n plus 1 minus 1 over n plus 1. And let's clean up the numerator. We get n, and the denominator's n plus 1. Okay. So this right here is our s sub n. This formula will, if we plug in n, give us the sum of whatever it is that we're adding, okay? So let's take, if I want to find the infinite sum, I want to take the limit as n approaches infinity. Of my formula, n over n plus 1. And I'm going to plug in infinity. I get infinity over infinity, which cues me to use L'Hopital's. So I get the limit as n approaches infinity of 1 over 1. And that is just 1. So this particular telescoping series actually adds to 1. If I add up every single term, I'm going to get 1. Any questions on example number 5? All right, so let's have you folks take a look at example number 6, all right? This one's already in sigma notation. It says determine whether this infinite series of 1 over n squared plus 4n plus 3 converges or diverges. If it converges, find the sum. So knowing that this is in the telescoping series section, let's go ahead and use partial fraction to rewrite our a sub n. Okay. So take a moment to write the thing highlighted in the red as some partial fraction. All right. Hopefully we were able to factor that denominator to get n plus 1 times n plus 3, okay? If you're still not feeling confident in your factoring at this point in your math career and you plan to continue to go further, I would make sure that you get comfortable with it, okay? It is definitely one of those things that never goes away. So what are some nice numbers I could pick to find my A and my B?
-3 and -1.
-3 and -1, okay. So in one case, I'm going to get 1 equals 2. B. Oop. I wrote this backwards from my note. 1 equals -2b, excuse me. And that means b will equal -1/2. And in the other case, I should get 1 equals 2a. And that means that a equals 1/2. All right, so if we plug those back in, we're going to get 1/2 over n plus 1 plus minus 1/2 over n plus 3. So we're going to use this in place of our original expression, okay? And when we do that, let's see, let's shrink some of this. So when we rewrite it, we can actually pull the 1/2 out to the front because essentially sigma notation leads right into integral, okay? So I'm going to take the 1/2, I'm going to pull that out to the front, the sum from n equals 1 to infinity of 1 over n plus 1 minus 1 over n plus 3. And so we can start to write out a few of the terms. So we'll leave the 1/2 in the front. And we're going to start by plugging in 1. So I've got 1 over 2 minus 1 over 4 plus, when I plug in 2, I'm going to get 1/3 minus 1/5. Okay, so at first, right, I've only written out 2 terms, my a sub 1 and my a sub 2. Nothing's canceling out so far. Excuse me. Excuse me. So since things are not canceling out, let's try a few more terms and see what happens, okay? So plus, what happens when I plug in 3? What do I get?
Then you get your 1/4.
1/4 minus 1/6 plus, when I plug in 4, I get 1/5 minus 1/8, right? And I keep going if I have the infinite series. Now, this negative 1/4 does cancel out with the one that I believe it's James said, oh, there's the 1/4, right? So the negative 1/4 and the 1/4 cancel out.
1/5.
1/5 and the 1/5, right? Negative 1/5, positive 1/5, okay? So as we're sort of canceling these out, you might start to notice that we end up with the first term, right? We have our 1/2, we have our 1/3, but then a bunch of the other ones are going to cancel out. But let's see what happens when we get to the end, okay? So I'm going to put the dot, 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 and then let's write in like the nth term. So the nth term would be 1 over n, sorry, the n minus 1 term. So 1 over n minus 1 plus 1 minus 1 over n minus 1 plus 3. So this is my a sub n minus 1 term. And then let's add the a sub n term, 1 over n plus 1 minus 1 over n plus 3. This is a sub n. Okay. Now with the 1 over n, this one is going to get canceled out. But this one doesn't have anything that comes later that will cancel it out. Okay. Now, a few terms ago, there was an n plus 1. So this one also gets canceled out. All right. So when we look at what we have left, and I did not leave myself enough space, we have 1/2. We have our 1/2 plus 1/3 from the beginning. Then we have our minus 1 over n plus 2, because n minus 1 plus 3 is n plus 2. And then we have a minus 1 over n plus 3. So it's a little bit different than last time. But when we think about what happens as we approach infinity, so as n approaches infinity, what happens to this n 1 over n plus 2?
Zero.
This is going to go to 0, which means this is also going to go to 0. And so we'll end up with 1/2 times 1/2 plus 1/3, which is 1/2 times 5/6 or 5/12 as our sum. So some of the telescoping ones are like example number 5, where like you can see immediately things are going to cancel out. And some of them are like example number 6, where you might need to be a little bit more patient and see if things are going to cancel or not. Okay.
Can I ask a question on that?
Yeah.
How did you know to use a to the n minus 1?
So if I know that things get canceled out, like I'll write out a few in the beginning, but then I might even go back as far as a sub n minus 2. So I can go back as far as I need to get a better picture of what cancels and what stays. But in general, I like to go back at least one term to kind of see what cancels.
Okay.
Okay. Okay.
Professor?
Yes.
I just had I can't remember, why is it that that it's negative 2b? Like that's where like I got the one thing I kind of can't figure out. Why was it negative 2b? Like all the way back in the partial fraction part.
Yeah, because we plugged in -3 for n.
How did you know to do that? Like I'm seeing drawing a blank.
Well, to the folks who maybe answered that question, how did you know what numbers to pick?
You make, it's kind of like when you make x equal to 0 to find intercepts.
Oh, okay. Thank you.
Cool. Good teamwork, guys. All right. So are there any other questions on 5 and 6 before we take a look at 7? Okay. So let's take a look at 7, okay? So I see this infinite series, because I start at 1 and go to infinity, of n minus n plus 1. And so since we're in the telescoping series section, let's write out a few terms, and let's maybe write out a few in the beginning as well as more than one at the end, like maybe an a sub n minus 1 and a sub n minus 2, just to kind of see what we get. And so if we write out a few terms, okay, we will get, let's see, 1 minus 2, right? 1 plus 1 is 2. Plus, what do I get when I plug in 2?
2 minus 1.
2 minus, yeah, 2 minus 3. Okay. Now, I know you guys know what 2 minus 3 is, but I think it's really important for us to kind of practice like writing out multiple terms so we can kind of just see what the greater pattern might be. And let's write one more with the numbers. If I plug in 3, I get 3 minus 4. And let's see what happens if we have a sub n minus 2. So what would I get if I plugged in n minus 2 everywhere I see an n?
-1 plus.
No, I want you to plug in n minus 2 everywhere you see an n.
Oh, okay. So n minus 2 minus n minus 2 plus 1.
Minus n minus 2 plus 1. Okay. So that's like what we could say for a sub n minus 2. Plus, let's see what we get when we write a sub n minus 1. It's going to be n minus 1 minus n. Poor spacing on my part. Let's write in now our a sub n. So that will give us n minus n plus 1. So I would say that for series, write out as many terms as you feel like you need to kind of see the pattern, which I know some of you already see the pattern, so thank you for your patience. But it's up to you how many you do, okay? Now let's see, things that cancel. This -2 and this 2, this 3 and this 3, 4, and there's gonna be a 4 that cancels out, right? That means that this n minus 2 will cancel with something from before, but I have a negative n minus 1 and a positive n minus 1, and a negative n and a positive n, okay? And so when I see what's left over, I have a 1 from the very beginning, and then I have nothing again until I get to this minus n plus 1 at the end. Now, when I simplify this, what do I get?
Negative n.
Negative n, okay? So what does that mean? Does this sequence converge? Does this sequence diverge?
Converge.
Diverge.
Okay. So for the folks who are saying converge, why do you think that it converges? And on the flip side, if you say diverge, why do you think it diverges?
At the beginning, we talked about how the infinite sequence converges to the right. But if it's negative, that means it will be going to the left, so it wouldn't be able to converge, right? Or
So,
that's how I feel about it.
okay, thank you, Karen. All right, so Kevin says it diverges because it goes to negative infinity. What do folks think about that?
Wouldn't it diverge because n is equal to 1 in our summation, and because we found out it's negative n, wouldn't we just put in 1 there, so it's -1?
But -1 is a number that would mean it converges. No?
Oh, I'm thinking of like the r value. Sorry.
But there's no r value because it's not a geometric series.
Yeah, sorry. That's like, never mind.
Okay. All right. Now, I noticed some people saying -1 earlier on. Where were people getting that from?
I think they're getting that from the index.
The index being 1?
Yeah.
But how do they get -1? Every term has a -1. Yeah, okay. So one of the things that, we sort of skipped before we jumped right into like, oh, this is telescoping, so we must have to write out and kind of see what happens. Let's go back to our original equation or expression. I had n minus n plus 1. Now, if I were to use one of my go-to strategies, which is like, let's simplify things before we start embarking on a journey that we may or may not need to embark on, I would distribute that minus sign. I'd get n minus 1. And I would have, the sum of n equals 1 to infinity of -1, right? Because this n and that n actually go away. So if I have -1 and I'm adding that, how many times am I adding -1 to itself?
Infinite times.
An infinite number of times, right? Because I have to plug in 1, I have to plug in 2, I have to plug in 3, and I have to add them all up together, which is how we get this -n. And so now if we think, okay, let's take the limit as n approaches infinity of -n, we're going to get -infinity, which means that the infinite series, in this case, diverges. Okay. So if we sort of zoom back out for a moment and take a look at these 3 questions. So I think the first one, example 5, is very classic telescoping series, in the sense that, like, okay, when you first look at it, maybe it doesn't seem like it's going to go to anything, or maybe you think it's going to go to a number, but you're not sure what that number is. But with a little help from partial fractions, we can sort of set this up and see that, in fact, all those middle terms cancel out. And what we get at the end is a formula for the sum. Okay. Now, again, most types of series don't give you a formula for the sum quite so easily. And we just kind of end up with either converges or diverges. But for these special cases here, we're able to find an actual sum. Okay. Now, example 6 was just like, okay, well, sometimes we need to be a little bit more patient. We need to see which ones actually cancel out, which ones actually stay. And then number 7 is really there because I want us to remember, like, or realize that just because it's telescoping, like it's like something minus something else, doesn't mean it's going to converge. Sometimes it will diverge, and that's okay. But not all telescoping series converge. Okay. All right. So let's take a look at this last section here. Okay. So this last type of infinite series that we consider a special case is called the positive term series, and then there's a subset of that called the harmonic series. Okay. So a positive term series, or we often call it a P series, they are infinite series of this form. 1 over n to the p. And so you'll notice here that I didn't put n equals 1 and n equals infinity on the top. So I'm sort of assuming we're talking about an infinite series. All right. Now, when that exponent, so let's make sure we know p represents the exponent. All right. When the exponent equals 1, it's a special case of the p series. And we call this one the harmonic series. Okay. So even though it says positive term series and harmonic series, the harmonic series is just the special case where the exponent equals 1. So in general, p series are convergent if the power is greater than 1, and divergent if the power is less than or equal to 1. Now, we're not going to talk about why today. We're actually going to talk about the why tomorrow. But for right now, I just want us to know that a p series converges if that power is greater than 1, and it diverges if that power is less than or equal to 1. Now, unlike the other 2 special cases we saw, there's no simple way to find the sum for a convergent p series, okay? And this is actually going to be true about all the other series that we look at. So from now on, we're going to focus on determining just whether a series converges or diverges, okay? unless it's geometric or unless it's telescoping, we're going to say just focus on if it's converging or diverging. All right, so with that being said, let's take a look at just a couple examples of the p-series and see if we can tell based off of this rule whether they converge or diverge. All right, so example 8.
Diverges.
It diverges, and let's call this the harmonic series because p equals 1, and that means that it diverges. Okay. And again, tomorrow we'll talk about why that is, but for today, let's just go with, all right, let's look at the power, and that's what it is. All right.
P is the, sorry, but P is the power of n?
Yes. Yes,
Okay.
sir. Mm-hmm. So if I were to zoom in and put a little exponent there, we could see that that's a 1. All right, what about example number 9?
Converges.
Okay, so P equals 2, which is greater than 1. So we know that this P series converges. All right, what about example 10?
Converges.
P equals 3. 3 is greater than 1. So it converges. What about example 11?
Diverges.
What's the p-value here?
1/3.
1/3. All right. And that's just because we have the cube root of n is the same as n to the 1/3. Okay. So those of you who had me way back in Calc 1, like on the second day when I was like, you need to know how to do this, like it definitely carries through, okay? So we've got p equals 1/3. 1/3 is less than or equal to 1. So this p series diverges. Okay. All right. So that's p-series and harmonic series in a nutshell. All right, so we're going to be using these 3 special series pretty often over the next few days and also a little bit into next week, because we're going to end up comparing a lot of the more complicated series to the p-series or a harmonic series or a geometric series. Now, it turns out that if we know these ones really well, we can actually predict the behavior of more complicated series, like the ones we're going to take a look at tomorrow and on Wednesday. Okay. So I know that we didn't take a break today. We kind of plowed on through, but that's the end of the lesson for today, okay, for 11.2. And I think this is a good stopping point. This is where the quiz goes until. So the quiz is only on 11.1 and 11.2, okay? And then tomorrow we'll pick up with 11.3 and 11.4 on Wednesday, and that'll sort of round out the content that's going to be on exam 4, okay? Are there any questions on these notes before I stop sharing the screen?
I have another question on number 6.
Sure, what's up?
So on number 6, I get that you sat there and you started to find the terms to see, okay, where is my starting term going to start canceling out with all the other ones, and then whatever's left, that goes to the general equation. And then you went to the a minus n.
Yeah.
Started plugging in versions of a minus n to see what's going to be left over and what's going to cancel out.
Mm-hmm.
And so if I would have continually plugged in a to the n minus 2, then a to the n minus 3, then that one where you have 1 over n plus 2, that's the only one that would have been left?
Correct.
Okay.
Yeah.
And then you just, is there a reason why you've went straight to the end of a minus n? Is that just generally what you need to do in a telescopic or telescoping?
In general, a sub n is,
typically where you at.
Yes and no. Sometimes it's helpful to go to n+1.
Okay.
Yeah.
So then those should be sort of like my go-tos. If I'm not seeing the general equation,
Yeah.
plug in numbers, see what's left over, plug in a to the n minus 1, and then go to the a to the n. And then if I'm still not seeing it, then try a to the n plus 1.
Yeah.
Okay. I can do that.
Okay, cool. All right, any other questions on the notes from today? Okay, then I'm gonna stop sharing the screen. We're gonna